Welcome everyone to this new webinar offered by AGN Company. AGN Company is a solution partner of Dymola Systems software company. In this webinar, we will be interested in the design and the control of a air handling unit using the multiphysics software Dymola. I am Gaël Caron, and I am a simulation and modeling engineer for AGN Company. Let me first introduce AGN in few words. We are based in France, in Belgium, and in Singapore. We offer our clients various services, but for now we're gonna talk about systems engineering. Talking about AGN general positioning in systems engineering, we would like to support industries in their continual improvement programs to reduce energy and matter consumptions, reduce development time of systems, decrease stop time of production lines, redefine strategies of control, optimize manufacturing processes, increase knowledge and decision-taking capabilities in design spaces, and facilitate validation of complex systems. To do that, we use a so-called methodology model-based system engineering, MBSE. With MBSE, we have tools and we have methods as well. So, for our tool, we use modeling and simulation program and software to embrace the entire complexity of your physical processes and include the control strategies. We use as much as possible fully dynamic models, and we encapsulate specific know-how from you in easy to use and white box model. The methods around we can use are design of experiment campaigns and sensibility analysis, optimization algorithm, and reverse engineering. To do so, AGN developed partnerships with Dymola Systems. We are value-added reseller for 3 software. The first one is Control Build, which is used for the design and the validation of automation systems. We also have Rectify, which is a tool for management of requirements in a non-intrusive way. And Dymola, which is a software for modeling and simulation of complex and multiphysics systems. Here you have an overview of how we can use these 3 software together in a design cycle and in your working environment. In this webinar, I will demonstrate how to simulate and modeling a air handling unit with the software Dymola. So basically, our model will be composed by one air handling unit and 3 rooms and one control part for the whole model. We want to control the temperature and the pressure inside the room, and we will want to control the flow inside the air handling unit with this control part. So to demonstrate how to do so in Dymola Software, I will first investigate with you some components that are provided with the software from the fluid library. So first we have closed volume and open volume. We can also have pipes. We could have access to model for pump. We also have valve, discrete valve, and some generic resistance or pressure losses. And some sensor to measure the pressure, the density, the temperature inside my fluid, or the volume flow rate, for example. So first of all, we will design the room model that we will use for the entire model. So to do so, I use a closed vessel for my room, which is supposed to represent the volume of air you have in your room. Here you can find the volume in the room. I will also add some interfaces or ports to exchange air between my room and, first of all, the input of air from the air handling unit, the output of air to the air handling unit, but also some leaks here and some exchanges of air through the door, which can be opened by operator in the room. All these components are easy to find in the Modelica fluid library, and you just have to drag and drop it as I'm doing now. Okay. Other parts for our room, we want to take into account the heat transfer. To do so, I use a heat port from the Modelica heat transfer library, which is here, and you can find a heat port here to exchange heat flow through my room. I will also use a convection model, which is here, also here in the heat transfer library, convection here, and I will parameterize the heat transfer convection with some parameters which define my room, the internal walls area and the heat transfer, external wall area, heat transfer, etc., etc. I will also have some heat coming from processes and lighting in my room. To do so, I use here one heat flow in my room, which is parameterized with this input with the number of processes on, this input which is the number of people in the room, and this which is the lighting on or off in my room. I also have a sensor of temperature to measure the temperature in my room, and the same to measure the pressure in my room. I can show you here some equation that I wrote by hand to define the power given by people body in the room, the power given by lighting, or the power given by the processes in the room. I also have some parameters to define completely my room, and I will show you how I can parameterize easily my room now. So to do so, I just drag and drop the model I showed you before here, and we will parameterize my room by double clicking on it. Here I have several parameters from my room, and I can also choose the medium that I want to use. It means the thermodynamic table of the medium inside my room. So for me, it will be air with a simple dry air model. I also fixed the temperature outside my room to have heat exchanges of 22 degrees Celsius. And here have some processes on and some people in the room, and the lighting on and off, which is controlled by this component. If I go through simulation, I will now post-process what happened in my room. It's very easy. I go through room and I can look at the temperature in my room, which is here. So at the beginning my room is 20 degrees Celsius, and after the temperature increase by step depending on the number of processes on or people coming in the room. For example, here we have the number of processes in the room. We also have the number of people in the room, and we can also have a look to the lighting on and off. I can also post-process the pressure in my room with no leak, and here is the pressure in my room. Everything has been automatically computed by Dymola using the thermodynamic table of air. So here you have the pressure, and we also can see that it follows the same with temperature, same behavior. Okay, this was the first step, and now I will go through other things, and I will add some airflow in and airflow out in my room, and some leaks here. The leaks are parameterized using pressure loss here, zeta, that can be found in the Modelica fluid library here. And I will also parameterize a valve open and closed to simulate a door opening and door closing. Now I will simulate the same model. Now in my new model I can now post-process the pressure inside my room, which is slightly different because I have flow in and flow out in my room. Let's see how it goes for the temperature in my room here, which is slightly different as well. I can also post-process the flow inside the different interfaces of air. So for example, this one, I have a constant flow in the input, and for leak I have a non-constant flow, and the flow could be positive and negative, which means that air is going from the room to the external air, or from the external air to the room. And for the door now, door volume flow rate, I have some peak because I have some losses of air when my door is open or open by an operator. So now we have a fully tested model of room with both heat transfer and air transfer, which is mass transfer, and we will define a new model to go a step further for the simulation, and the model will be a air handling unit input part. So you can have a look now how I design my air handling unit. It's basically the same idea. I used only components from the Modelica fluid library. I have external fresh air with a defined pressure and defined temperature that are parameterized. I have a pipe to go through a pump, and I have here a controller for my pump. After the pump, I will have 3 different heat exchangers. The heat exchangers are for the chill loop to chill the air inside my air handling unit, the hot loop to warm the air inside my air handling unit, or another heat exchanger for an energy efficiency loop. The different heat exchangers are parameterized that way. I will choose one medium for the air, one medium for the chill fluid, which will be for us water, and I will choose a heat exchanger effectiveness of 70%. Same for the other. I also have here a linear valve to control the flow of chill water inside my heat exchanger, and I have the same valve linear here to control the hot water inside my hot loop. And finally, I have 3 interfaces to exchange air with the room number 1, room number 2, and room number 3. I can measure the temperature inside my room using this sensor. Now we will test this new model of air handling unit input. The model I just showed you is here. I just have to drag and drop, and I have the entire model here with all the interfaces. So to test this model, which is here, I will go through parameterization. So here I can choose the external temperature of air, the water source temperature for cool part, the water source temperature for hot part, and several thermodynamic table for my air and the water inside my different loop. I will now use the same model as I used before, the room model that I showed you before, which is here, and drag and drop it and plug it through this interface for air transfer to the air handling unit. One is there, one is there, and one is there. I will also add heat transfer inside my 3 rooms, and I parameterize for the pump inside my air handling unit as a ramp, and also a ramp for cold water and a ramp for hot water, and we will see how it goes through the different room that I have defined. So I will go through simulation now. The model has been computed, and we will first see what happened in the air handling unit in terms of flow. So this is the flow inside my air handling unit. So I have a kind of ramp here and a final value here, stabilized value here. I will also post-process the temperature in my different room to understand the effect of cold water and hot water. Here are the different temperature in my different room. I can see that the different temperature are due to the control of cold water flow here and hot water flow here. So here you have a decrease on temperature due to this cold water ramp, and here you have an increase in temperature due to this hot water ramp. So our model will become more and more complex now, because we will add a new part for the air handling unit, which is the absorption part. It's basically the same idea as the input part, and I will have 3 interfaces from air coming from room 1, room 2 and room 3, different pressure losses, a heat exchanger for energy efficiency, and a pump that I can control here, and a boundary condition, which is the external air. Now I can plug together my input air handling unit and my output air handling unit, which is absorption part, to my 3 room. And now we will demonstrate that the different room has different pressure due to the input flow here, which will be constant, and the output absorption part here, which will be constant as well. So let's compute this model. We want to see the different pressure in the room now. So this one is the pressure in the room number 1. This one is the pressure in the room number 2, and this one is the pressure in the room number 3. Here you can understand that due to different pressure losses over the 3 rooms, we have different pressure maintained in a room. Now we will go a step further, and we will add for the different part of my model some control part. For example, I will use a PID model from the Modelica library box, which is here. I have a PID model here that I can parameterize with again a time constant for integrator and a time constant for derivative block. So the first part for me will be to control here the flow inside the air handling unit input, and the flow will have to be a constant value of 1000 meter cube by hour. Here I can measure the flow through my pump, go to a feedback, use a PID, parameterize that way, and this PID will control the pump through a limiter. I will do the same for the absorption part, and for the absorption part I want to control the pressure inside my room number 2, and basically I also control the pressure inside my room number 1 and number 3, because we saw before that the relative pressure between room 1, room 2 and room 3 are constant. To do so, I will do the same using a PID here, and I want to control the pressure in my room 2 with plus 10 Pascal compared to the reference room, which is here. Here I have my reference room with sinus over the atmospheric pressure. So here is the atmospheric pressure, and I have a sinus with an amplitude of 10 Pascal. With this model, I will normally be able to control the flow through my room here, the renewal flow in my room, and I can also control the pressure in my room 2 and then room 1 and room 3. We will compute the model. So first of all, we will verify the flow through my pump here. You can see here that the flow has been controlled here to obtain a value that I wanted, 1000 meter cube by hour. And then we will post-process the pressure in room number 2. So you can see that the pressure in the room number 2 is a sinus, and we want to see the difference of the sinus with the reference room, which is given by feedback number 2. And here the pressure difference between my room and my reference room is given by this feedback, and we can also see that the pressure is maintained to 10 Pascal. Then the pressure in my room 1 and my room 3 follow the same sinus here. For room number 3 and for my room number 1, the pressure is given here. We can understand that the difference is again constant. We will go a step further now, and we want to add a controller for the water flow here. I use the same PID controller with a gain, and what I want to do is maintain a temperature of 15 degrees Celsius in my room number 2. I also had here some processes and some people inside my room. So at 500 seconds I will have processes on and people coming inside my room. Until 700, at 1000, same, I will have again processes on, and so on and so on. And we want to know if our air handling unit and the controller that we define are able to control pressure and temperature inside the different rooms. I simulate the model here, and we will post-process now the temperature inside my room 1, the temperature inside my room 2, and temperature inside my room 3. You can see that due to the different processes on and off, the temperature evaluate between 17 and 12 degrees, but at the end we obtain a temperature wanted of 15 degrees. And for the pressure we have the same, and we can post-process the pressure inside my room here, room 1, room 2, and room number 3. So this webinar is now over. Thank you very much for watching, and hope to see you again in another video. Thank you very much. So thank you very much for watching this webinar. If you have any question, you can contact me in the following address: gael.caron@adn.sg. Thank you very much, and bye.